Hello everybody and welcome to today's lesson on inverses and composition of functions. Our objective for today is we will investigate and analyze the inverse of a function and the composition of multiple functions algebraically and graphically. So first of all, what is a composition? For me, the best way to think about it is we are plugging one function into another. Plugging one function into another function. Let's look at our function machines here on the right. First, our x goes into the function machine g and comes out as g of x. And then that g of x goes into the second function as an input now. And that second function f turns that into f of g of x. And that is, by the way, one notation that we can write compositions of functions. There are two different ways. We can write it like shown here, f of g of x with a whole bunch of parentheses, or we can also write it f, and it looks like fog, f of g of x. When we have compositions of functions, we have to be extra careful with our domain. X must be in the domain of g. In other words, up here, remember, our input must, of course, be allowed to put into the function g. And then g of x must be in the domain of f of x. G of x is now our new input, and that, of course, also has to be allowed to be put into the function f. This means that we have to check our domain restrictions before we simplify. Now, please make sure you write this into your notes. All right, then let's look at some examples. Here we have three functions that we are going to create compositions of in different ways. I'm going to use different colors. My f of x is going to be in pink. My h of x is going to be green. And g of x is going to be orange. So, in the first step, we're supposed to find f of g of x. Well, g of x was 5x minus 2. In other words, the function g does to our x, multiplying it by 5 and subtracting 2. Now that becomes our new input into f of x. And what does f of x do with our input? It takes the input, squares it, and then divides 4 by that value. And here's our composition. Now let's check for domain restrictions. Since we have the x in the denominator, we have to make sure that we don't end up with a denominator of 0, right? That can't happen. So what value would make that happen? 5x minus 2 is equal to 0, which means 5x is equal to 2, which means x is equal to 2/5. So that is one number that cannot be in our domain. Let's take another look at our function, 4 over the quantity of 5x minus 2 squared. Nothing we can really simplify here, so this is our final composed function. And our domain is x such that x is not equal to 2/5. That's that. Okay, in our next example, we're supposed to find g of f of x. So this time we're going to start off with f of x. F of x, we said, is 4 over x squared. And we are making the composition this whole function, the input gets multiplied by 5, and then 2 gets subtracted from that. Before we simplify, let's look at our function and let's look for domain restrictions. And here, x cannot be 0, otherwise we would divide by 0. Now, we can simplify this function a little bit. 5 times 4 is 20, so 20 over x squared minus 2 is our g of f of x. And taking a look at g of f of x, we see that x not being 0 is still the only domain restriction. So the domain is x such that x is not equal to 0. Okay, on to the next examples. Now we're supposed to find g of x. You're probably thinking g. Okay, so g of x is 5x minus 2. Now putting that back into g, we have to multiply it by 5 and subtract 2. Looking at this function, do we see any trouble with any possible inputs? Nothing really. We don't have any denominators that can turn to 0, or any radicals that may end up with negative numbers under them. So no domain restrictions. We just go ahead and simplify this function. 5 times 5x is 25x minus 10 minus 2, or 25x minus 12. And our domain is x such that x is an element of the real numbers. All right. And now we have f of h of x. H of x, our function in green, takes the input, subtracts 2 from it, and takes the square root of that. And now f of x takes that input, squares it, and divides 4 by that number. Alright, then let's look at our denominator. Since we're talking about domain and graphing here, we cannot have a negative number under the radical, because we would end up with a complex number that can't be graphed. So first off, x has to be a number which is greater than or equal to 2. Alright, that's good to know. And now we're going to go on and simplify our function. We only can simplify in the denominator. The square of a square root. The two functions are inverse functions, cancel each other out. We got 4 over x minus 2. Now we still have a denominator that is not allowed to turn to 0. And how would it turn to 0 now? Well, if x was equal to 2. So x is not allowed to be equal to 2. And since our function is fully simplified now, we have all our domain restrictions. X such that x is greater than 2. Now here I want you to notice that if we had simplified first and just ended up with our domain restriction x is not equal to 2, we would have missed a whole lot of things. Remember, we had a square root in the denominator in our function before simplifying, and that told us that none of the values can be less than 2, not just 2, but less than 2 also, or we wouldn't even have been able to make that step to our simplifying. So that's why it's important to check your domain restrictions before you simplify, or you may miss out stuff. And then those domain restrictions combined end up down here telling us that x has to be greater than 2. Not just not 2, and not just greater than or equal to 2. Okay, so much for this. Now go ahead and watch the second part of this tutorial.